So now let's go back and look at the cost function for linear regression. Recall that we're going to define an aggregate cost function over all of the training data by averaging the pointwise training error. And training error we can understand very easily as looking at a specific JF example. Let's say xij, the inputs. We're going to take the learned vector of weights, times it by that to produce the signal. Okay, and then that's the predicted value. We're going to subtract away the actual value, the ground truth that we have labeled. This is yj, and then take whatever difference it is, hopefully very small, and square that, and that will be our squared error. And this is the form that we have for an individual instance in this part of the box. So that's the expression done for individual instances, but we can also write it in a vector notation. It's a little bit more compact and easier to understand, right? We're just going to have a norm version of this, which is over here. And so we have a large matrix X, which is all of the training examples. It looks a little bit like what we see over here, right? Where we have the first one, the second one, the third one, all the way to the last one, the mth one, stacked on top of each other as row vectors. So we have to transpose them. Then we are going to take the weights theta and then do a dot product with each of them so as to get the signal, right? Basically what we have up here. So we're going to take this multiplication between the weights and the observations. We're going to get the predicted value, and we're just going to subtract away the column vector of the ground truth outputs. Okay, and that's going to be what we are going to get inside of this norm, right? Inside of here, we're going to square that value and then again average it. So we have this over here. So you should be able to answer this question very easily. What are the dimensions of X, right? And in fact, our X matrix here is going to have all of the components N, but it's going to have an extra dimension, right? And hopefully you remember why, because this is our bias term or our intercept, right? So we're going to add that as our X0. And then these N dimensions are going to be from X1 all the way to Xn. Right, all of the individual dimensions of the features that we are putting in as the observations. So this is a cost function, so we need to minimize it. So what can we do to minimize? Again, if you recall from gradient descent, what we have some cost, let's say J train on the y-axis, and we have different values of parameters theta. We saw how we can think of this as some type of manifold, but let's say we only have a univariate case, then it would be something like a convex surface like this. And it's a convex surface because we're taking a convenient form, which is the squared error, which has a single minimum. And that leads us to the very clear idea that we're going to find the bottom of this analytically by looking at the case where the gradient is 0, right? So if we can understand that, so this is going to lead us to this formulation where we're setting the derivative or the gradient to 0. So all we're going to do is take the analytic derivative in all of the partial directions that we have that represent the x. So you can actually do this out algebraically and do it not in the vector form. You can do all the partials, and then you're going to find after you gather all of the partials that you're going to get back when you reassemble it into a matrix notation, you'll get this. And basically we can understand this very easily, right? We're going to take the square, we're going to move it outside, so we're going to get it to come down over here. So this is our 2m. And then because we're differentiating with respect to theta, we're going to multiply against the constant, which we're going to bring outside, and it's actually going to be x transpose because it's a matrix and not a scalar. So we'll get x transpose x as the term. And we're going to keep the term itself, so that's getting a copy of what's inside here. Okay, So what we want to do next is just move this part of the equation to the right hand side. So we're going to move it over by taking this out. Because it's moved over to the other side, it's no longer negative, and we'll get x transpose x theta. And because we have constants on both sides of 2 to the m, they can drop. Okay, so that's what we're showing you here. The next thing we want to do is be able to solve just for theta, because that's what the closed form solution we're looking to get here. So how do we do that? Well, it would be nice if we could take this particular matrix, right, and find its inverse. Then we could just multiply it times the inverse, and then these things would cancel out, and then we'd get theta alone for that. In fact, x transpose x has an inverse because we have x here, which we are going to just draw out as this rather tall matrix, and x transpose is of course the same matrix, just put on its side. And when we times this out, we're actually going to get a small matrix of the same size that we just talked about before, n plus 1 by n plus 1. So this is not a very large matrix. It's just telling us that the matrix that we have has the same magnitude as the number of features that we are putting on each input instance. Right? So this is what we're getting from this, and we're times our weights, which is another column of 1 by n plus 1. And that's going to be equal to what we have on the right hand side here. So in order to get rid of this matrix here, this one in the blue rectangle, we want to times it by its inverse. And if we can get that to happen, then we'll get rid of both terms and we'll be left with theta on its own. And so we'll have another term here. So when we cancel out all of these things, what we have here is a closed form expression for theta. I'll just write it out here. Theta equals x transpose x, taking the inverse times the transpose of x, y, right? So this is what we want to solve for. If we can build this solution analytically, we're just going to take whatever matrix that results from this bracketed form and times it by the column vector representing the ground truth, and we'll have an answer for theta. Isn't that nice? So this particular matrix we're going to examine in a bit more detail, the one in brackets. So we're going to call this matrix that we just wrote out as x dagger. And x dagger has a particular name that we're going to give it called the pseudo-inverse. And you already know, because we have a rectangular matrix x, which is pretty tall because we have a lot of examples compared to the number of features, usually, that this is not invertible, it's not square. But in fact, we can think of x dagger as a pseudo-inverse because if you can add x on the right-hand side of the pseudo-inverse on both cases, what we'll see is, oh, look at this, this term over here, that's the same. We have its inverse over here. We multiply that. You're going to get back a matrix that's an identity matrix. So in some sense, we can think of it as an inverse, even though, of course, x being a rectangular matrix doesn't have a proper inverse. So I also want to explore the pseudo-inverse with you to give you some intuition why it's computationally interesting. We're going to start with x, which is our very tall matrix of examples, where each example is one row, okay, all the way down to the last example. And we also have x transpose. And when we multiply these two together, we're going to get something nice. It's going to be a small matrix here that we're going to invert. Okay, it's only going to be of n plus 1 by n plus 1 dimensions, basically on the order of the number of features, right? And so because we oftentimes will do a nonlinear mapping or take the raw signal and represent it using useful features in a compressed fashion, the number of features that we actually give to a linear classifier might be not terribly large. In this case, performing this inverse operation, which I'm sure you know, an inverse matrix operation is on the order of cubic, right? It's a pretty expensive operation, but at least we can see it's only reliant on the magnitude of the feature vectors. It has nothing to do with the number of rows or the number of instances in my data set. So that's sort of nice. It's saying that, even if I have a large data set, the computing of this particular term here, the inverse of x transpose x, is going to be not bottlenecked by that amount. We're also going to have our x transpose over here. Okay, we're going to times these two together, and we're going to end up with a matrix that's of the same size, right? So it's going to be exactly the same form as that, represented by this thing over here. So now we've come to a closed form solution for linear regression, and this is how it works. The first step that we're going to do is construct the matrix X. We're going to stack all of the examples on top of each other, and we're going to build the vector for y from the first ground truth all the way to the nth, right? And then we're just going to simply compute this pseudo-inverse, this x dagger, by taking the transpose of x, timesing it with x, computing this expensive order n cubed operation on hopefully what is a small matrix if we don't have a lot of features, and then again timesing that by the x transpose. Great. Once we have that, we're going to return that multiplied against y, and we're going to have our weights theta. And so this is really interesting, contrasting it with what we learned for linear regression and the perceptron, which is iterating over a number of simple steps many times, perhaps hundreds of thousands of times, to find a good linear separator. We're doing this analytically by taking the derivative and going directly to the optimal theta. So you can think of this as normal equation for linear regression, where we get one-step learning. We just do this particular 3 steps, which is only bounded by the computational complexity of the number of features in cubic form, and then we're going to compute the solution. There's no iteration necessary, it's just closed form. So in summary, we found 2 different ways of computing solutions for linear regression. Right now, we found the normal equation, which is a closed form solution, where we're just computing the inverse of x transpose x and multiplying it x transpose to get our pseudo-inverse. And the nice thing about this is when the number of features is small, we don't have to do iteration, we don't have to worry about the learning rate. Those are all things that we have to worry about when we look at iterative manners. Even though we can use the normal equation to compute a closed form solution for linear regression, sometimes we still want to use gradient descent. And why is that? Well, when we have a very large number of features, then this order cubic operation is going to be expensive, right? And in certain cases where the matrix of that we need to invert, x transpose x, is non-invertible, for example, if some of our columns, our features, are not distinct, we have replicated columns, then we can't take an inverse. So there are some other cases which you can think about why x transpose x might not be invertible. Okay, you can post your answers to this on the discussion forum so that we can all recall from our linear algebra what are the cases why a matrix might not be invertible.